is that what you want to do is to fuse those two nucleus together, and they're both electrically charged, so they repel each other. So you have to throw them at each other with high speed. And high speed in a gas is actually the temperature of the gas, and you need a slight temperature of 150 million degrees C. And here lay the problem. So you can achieve that in the sun or in thermonuclear explosion, for example, but to produce that in a lab is very difficult. So you have to throw lots and lots of energy in the gas, and you have to make sure that this energy doesn't flow out of the gas very quick. When you hit this gas at this temperature, it becomes a plasma. A plasma is when the electron and the middle nucleus get split apart, and then you get this sort of soup with electron and ions swinging around. That's called a plasma. So they try to take this plasma, stick it in a magnetic field. However, there's turbulence and the heat escapes faster than expected. So the standard approach that have been pursued for a long time is to make bigger and bigger machine. Because if you have a very large blob of plasma, it'll take longer for the heat to escape. And that have led to increasingly expensive and difficult machine. And they are presently making a $20 billion project in the south of France to make the biggest machine ever. And most scientists think that that particular machine will start to produce energy, but it's so big and complex that the cost of the electricity that will come out of that might be a little bit out of range.
Boy, so basically the problem is trying to contain something that's 150 million degrees.
That's correct.
Well, what are the different ways in which scientists have tried to get fusion to actually work?
Well, as I say, there's the standard tokamak, which is a donut of magnetic field. So that's the most standard way. The second sort of contender is the laser fusion. You take a ping pong ball, you put the deuterium and tritium, which is the gas you're trying to fuse, in the ping pong ball, and you shoot lasers all around the ping pong ball, and you hope to make fusion this way. The main contender for that is the NIF, the National Ignition Facility. The NIF, for example, I think runs at about $6 billion nowadays. Now, in the 70s, Dr. Turchi at Naval Research Lab proposed something called MTF, which is magnetized target fusion. It's a bit in between. What you're trying to do here is you produce a small blob of plasma with electrical current flowing in it. That produces a magnetic field that keeps it together. And then you put that in some sort of metallic container, and you collapse the metallic container rapidly. You will compress the plasma with the magnetic field, and you hope to hit thermonuclear condition with that. So that was an extremely good solution. And here comes General Fusion. This is my company. And we did a slight little improvement to the system. So this is a new method that we're pushing, and we hope it can be done for relatively low cost compared to those billions of dollars of the other system.
Okay, so if these two problems of containing a material that's 150 million degrees and the amount of energy that you need to put into it being so high and so expensive, if those problems can be overcome, how will fusion change the world?
Well, fusion, one of the nice things about fusion first is the fuel. The fuel comes from seawater. There's seawater everywhere, so there's no problem with fuel. And also, if you make the machine itself cost effective, we are planning to have the machine to cost less than coal. Now, lots of people are proposing like wind and solar, and it's all a little bit more expensive. And they hope that because people want to save the planet, they're going to use that in place of burning coal. Now, we may do that in rich country like in Canada or the U.S. because we like the green and blah, blah, blah. But in other countries which are in development, they might not be so keen. And if coal is cheaper than whatever else, they will still burn coal. So the planet and the global warming is not going to improve very much. However, if you can make a clean source that's actually cheaper than coal, then even everybody will buy it because not only it saves the planet, but it's cheaper than the incumbent thing coal. So we are trying to make that so inexpensive that everybody, all the power plant that would be installed in the future would use that. And hopefully, with a bit of luck, the CO2 problem will be solved.
So is fusion still 50 years away?
No, we think that we can hit the power line. Like we're designing this project to show the core fusion reaction in about 4 to 5 years. And after that, it would certainly take another 4 or 5 years to make a real power plant of this thing. So we think we can hit power line in about 10 years, which is better than 50.
Certainly is. Dr. Leberge, thank you very much.
You're welcome.
Dr. Michel Leberge is president of General Fusion in Vancouver.
Interview 3 is now over. Interview 4 will begin now.
Okay, let's think of a few technologies that have already changed the world. Making fire is an obvious one. The wheel, of course.